I will travel where no man has dared to go.
The accepted laws of physics break down.
Boundary between the known universe and a place beyond the reach of science.
Alright, ahoy hoy Physics 2 students. So if you're on this last problem right now, it is a doozy. So once again, we have to find a ratio that exists in here, so not everything is given. We have to use logic in order to solve it. So we have water moves through a constricted pipe in a steady ideal flow. So that means no external friction, it's not compressible. The lower point shown in the figure below, the pressure is 1.7 times 10 to the 5th pascals, and the pipe radius is 2.5 centimeters, or 0.025 meters, with the highest point located at y is 2.5 meters. The pressure is 1.25 times 10 to the 5th pascals, and the pipe radius is 1.6 centimeters, or 0.016. Let's get started, shall we? Alright, the first thing you should do at home on your own is you really should draw a sketch of this and label everything so you make sure you have a clear idea of it. So, I'm not going to do that because I think at this point in your life you should be able to diagram stuff. You got enough to cover right here and I don't want to bore you with my drawing. If you need to know how to draw it and diagram it, to understand what's going on, let me know. I can help you. But, okay, the first thing we're going to have to actually do is we're going to think about how are we going to find, the first question is to ask for the velocity at V1. So the initial velocity of the pipe, where we have a, I'll draw it. So we have this pipe, it raises up. Understanding? So right back here in this area we have a pressure that's equal to 1.7 times 10 to the 5th power pascals. And let's see, this pipe, the radius here is equal to 2.5 centimeters. And let's see, okay, so we also know then that there's a pressure up here equal to 1.25 times 10 to the 5th pascals. And just seeing that lower pressure means I know that my radius has to be much smaller. The fluid is moving faster. That is 1.60 centimeters. Alright, and then the final thing we know is we know that between this point, this original point, we have a height difference. We have a delta y that is equal to 2.5 meters. Alright. I love these ones. So let's get started, shall we? First thing we gotta do is we gotta figure out what equations we're gonna use, and this just looks like we have, once again, fluid moving through an object, so we're looking for velocities. So it looks like we're going to do best with good old Bernoulli's principles. So let's start off with the big bad boy of this times 1.5 and a rho b squared 1 plus, and now we have to include in there the kinetic energy 1, or I'm sorry, the gravitational potential energy, because have a height difference. So, okay, so then we have this is equal to P2 plus 1/2 rho Alright, so now we have to rearrange this equation to solve for the velocities. Now notice I'm saying the velocities because we don't know either velocity. And unfortunately, the two interact with each other. So this pressure difference is going to, of course, have some effect on the flow of the water, its flow rate. So let's start deriving this big old bad boy. So we know we're going to want to have, we're going to solve from the standpoint of v squared 2. So let's start it with getting on one side v squared, v2 squared minus v1 squared. And if I derive it correctly, I should get canceling everything out, crossing everything out. I get, of course, I first start by getting rid of these halves. So I do 2 times, and you should be familiar with at least this first part. We've done this before with the delta p. So I'm always just going to put delta p there because I don't want to write too much. Divided by the rho, and in this case we don't know this. The rho of water, which you should be familiar with right now, is 1,000 kilograms per cubic meter. And minus gravity times, and I'm just going to put delta y, because it's y2 minus y1. Okay, so it's important that, that we see that this is the equation you should derive. Now, because we don't know either of these, we have to do one of those scenarios where we look to see, can we figure out based on a ratio, okay, what the other should be, and then substitute in later on. So of course, solving for 2 unknowns. Hooray! And if I look and I think about it, okay, so can I solve for this? Well, I can plug everything in this situation right here, and if I plug all of my givens in, my delta p, my rho, all of the stuff I get, I should get a 4.5 times 10 to the 4th power for my change. So I'll just write that over here so to help you guys follow along. This is a really nasty problem. I know I scratched my head for a while. Being my first time solving it, it was not fun. But this is what I want to do on a Saturday night. You know, it's like 9 o'clock on a Saturday night. We're going to get funky with physics. We're going to move it up. That's how we roll. Straight out of Bethlehem. 8 times 2.5. And when I solve for all of that, I should get 41 meters squared over. Alright. So now, kind of stuck. Where do you go from this? Do we have any way of solving for a ratio? We actually do. If you think about it, it's one of my favorite equations, the continuity equation. I just like it because it's just so logical and simple. And once again, that's just going to say to us A1 B1 is equal to A2 times B2. Alright, and if I work with that equation, I can actually rearrange everything. And let's say we're going to solve for V2, okay, since we originally started for. So, I'd say V2 is equal to A1 by A2, okay, times V1, and then take it a little bit further, and I can even think about, okay, so that means it's pi radius squared Right, so radius 1 divided by the pi, radius 2 squared. Okay. Times v1. And okay, so I can cancel out my pi's. No pi for divided by r2 radius, and that is squared times my velocity 1. Almost there, kids. And then if I think back to what actually my radiuses are, I just take my 2.5 divided by my 1.6, square that, and multiply that times by v1. And one step further, I get my 6.25 once I square it, my 2.56, and then multiply that times v1. So what I find is my ratio is that v2 is actually going to be 2.44 times greater than v1. Okay. So now going back to this, I'm going to go punch it back into my regular equation that I had earlier. So I'm going to go back to this equation up here, right in this area, and I'm going to do the v2 squared minus v1 squared is equal to, and I know it was equal to 41 meters squared over seconds squared. So now for V2, since I know V2, right, V2 is equal to 2.44 times V1, right? You get me on this one, kids? I can now take that and square it into this area. Okay? So I can take it into this area now. So what I'm actually going to be doing is I'm going to square the 2.44. Alright, if I do that, 5.95. Okay. Bear with me on this. And then I'm going to do a minus 1 times v1 squared. So once again, I have 5.95, right? That's what I got for squaring that, minus the 1. And why do I have to do minus 1? Because, well, they're subtracted against each other, right? The original statement was v2 squared minus v1 squared is equal to 41 meters per second. 41 meters squared over second squared, okay? So when I squared this, right, it's because I was substituting in, if you will, v1. So now I also took consideration that I had it already subtracted against the v1. So it's against itself. So when I do that, and now since I'm multiplying it times there, right, because the invisible one that always sits there, now I'm going to rewrite it over again to be equal to, okay, so just to be nice and neat, I'm going to write v1 that'll get confusing to you guys. So I'm going to rewrite it over again. I'm going to write it as v1, okay, is equal to the square root of 41 divided by, and I'm going to take this little part here, and since it's multiplied, I'm going to take it and make it 4.95. And when I solve for that, I should get 2.87 meters per second. Okay, the hardest part to understand here is, alright, so substituting it in there is not bad. That's not a very hard thing to realize, okay. So if I came up with 2.44, then I just go ahead and again do this in here. It's the minus the 1. right? Because we have to realize that when we do that, okay, I'm doing it there, and there's also one that sits in there. I know for me, that's the part I stumble on all the time. So now I have 2.87, okay, and that is my V1. So I solve for V1. Alright, now, this is a little bit easier. If you think about it earlier, I solved that V1, okay? The V2 is going to be 2.44 times V1. So now all I do is just go ahead and multiply them out. And I just take, well then fine. Then V2 is going to be equal to 2.44 2.87 from V1, and that should be equal to 7.02 meters per second. Oh, that one is tough. That's a tough problem. Look at the problem. Tough problem. So, in fact, I'm going to show it to my daughter who's walking by right now. Daughter, look at this problem, because I tell you to pay attention in math class. Do that, and these kids that I'm watching this video are very smart. You know why? They paid attention in math class. Okay, you can leave now. Leave. Just leave then. Okay, so the final step that we have. Are you ready? Flow rate. Love that. Love me some flow rate. Very easy. Got nowhere else to write it though. So I'm going to try and write flow rate here in a different color pen. And we'll use yellow. Alright, so flow rate. If you think about flow rate, as we said, is always going to be in... I told you it's one of the most important topics that we have. So flow rate. Not flow rider. Alright, flow rate right now is going to be equal to... We always know it's in meters cubed per second. So then we can also just really easily, how to get meters cubed per second. Oh, look, if I take an area and multiply it times the velocity, I get a flow rate. So I can just take any of the areas, and as long as I compare them with the actual velocity. So I can either do it for A1 or V1. Okay, or I can even do it for A2, V2. Either way, I can solve for my flow rate. So solving for my flow rate, I'm just going to go ahead and once again make sure you switch over your radiuses to meters, otherwise it'll mess everything up. Meters cubed. So if I just take my first flow rate, I'm going to take the sorry, I'm trying to do stuff where people are pulling games out from behind me. That's a little distracting when you're solving complex physics. Thanks. Sorry, guys. So I'm going to take my 0.025 meters squared times pi and then multiply. Someone just fell over in the room. And multiply it by my 2.44. And I should get a flow rate, in this case, that is equal to 0.0056 meters cubed. Not sure if you guys can hear this at home. My wife is laying down the lawn in the other room. It's nice. It's nice. And I'm doing physics and I just solve for a flow rate. So, once again, here, this is easy, right? Anybody can do this. Oh, just heard a dad has to go fix something. So, oh, my daughter just broke the curtain rod. So now we're gonna go actually do and apply physics to real life. So anyway, hope this helps. Rewatch this over again if you need to. Like I said, this is the answer. This one took the answer to number 1. Then over here is the answer to number 2. Right, the part B of it, and here's the answer to number 3. This one was the harder one. This was a little bit of the harder one. So anyway, I have to go and now fix a curtain rod. So, hope you guys... Saturday night. Look at that. Saturday night, 9/12. That's what I'm doing. Woo! Have a good evening.